Yeah. So I think we can start the session. So good evening, all. This is our fifth week live interactive session. So in this session, we primarily discuss about the support vector machine classifier. In that, we have seen how we can classify the binary, how we can do the classification task for the binary classification, and how. So there are some terminologies we have learned, which is an what is an hyperplane, what is an so in the support vectors, we have seen that the two factors, which are the marg- marginal plane and the hyperplane, right? Also, we have seen that how we can draw the hyperplane and how we can draw the marginal plane, and what is the necessity we require to draw a marginal plane, right? Also, we saw the some constraints, that is, and we need to find the hyperplane such that the marginal distance between the hyperplane and the closest point from the respective class, which should be the higher, actually, right? So in the lecture session, we have seen the explanation about the hard margin plane, which is an strictly classifying the uh, strictly classifying the classes, which, and there is another category as well. So there is a two way we can classify in the SVM, which is an first in hard margin and the soft margin. So in the hard margin, we are not allowing any instances or any point between the hyperplane and the marginal plane, right? In which we are calling or strictly classifying the instances. And in the soft hyper margin, we are allowing some instances which can be allowed in between the hyperplane and the marginal plane. So while discussing the question, we'll see what exactly the how hyperplane, margin hyperplane and the soft margin hyperplane has been drawn. Right? Okay, let's move to the questions. So this is the first question. The most of the questions here we are discussing in the related to the SVM, which is a support vector machine, which is about the classifier. Support vector is also used to regression task as well. Okay, we need to predict the values. So for that task as well, the SVM can be used. So but we have seen the discussion, or we have learned about the SVM for the classification task. In specifically, we have seen the hard margin binary classification. Okay. Yeah. So the first question states that a margin of hyperplane is defined as the angle it makes with the axis. The B option is that the intercept it makes on the axis. C option is that perpendicular distance from the closest point. Closest point means which is either it is respective of the classes. Perpendicular distance from the origin. Yeah. So what do you think that which one is correct option? Which option defines that this is an margin of hyperplane? Okay, let me recall the concept of the margin here so that you will quickly understand what exactly the margin is. So we have a, let's take as an 2D dimensional, that is an this is a x1 feature and this is an x2 feature, right? So here are two classes are there. We have studied the support vector for the binary classification specifically, so we are taking the examples related to the binary classification. Okay, so that you will get easily understand the concept. So here one specific class. Okay, and here is another class that represents as an cross and uh, the circles. Okay. So as we have seen that we need to draw a boundary line, which is a separable line in between the two classes, so that we can easily separate or classify uh, any new point in new point. These are the training points with respect to x1 feature and x2 feature. We have plotted uh, these training points, and you can see we are directly observing that they are clearly separable, these 2 points. So the svm is works like that. So it finds the separation space, and in that separation space it draws a hyperplane. So this is an separable boundary. Actually, we are calling that separable line is an hyperplane. So for this line we are calling as an hyperplane. Okay. So how we are calling the so how we are drawing this hyperplane, because there are many possibilities you can draw a separable line, a separable boundary. Okay, like this way, these are also separable lines, right? So these lines. So why only we require only this middle line only? Okay, so there is some analogy behind this drawing a line actually. So there is a one concept which is an margin actually. So we need to find from this subset which one is an closest to a separable boundary line. So this is an closest point from this positive from this class, and from this class circles class there is this is one uh, closest point from the separable space actually. So we need to draw a line here as well, that is a margin line which passes bit from the closest point uh, from the separation boundary line, right? So the distance between this separable line and this the closest point from this class should be greater. That distance should be higher actually, and we need to adjust this line such a way that the distance between the from this side, this is the left side, and the right side should be equal. Okay. So if you are drawing, let's take as another color. If you draw a line like this way, you can observe here the distance between this closest point, the distance between this closest point and this closest point is very low. So this is not a good hyperplane. So in the training process, this hyperplane is adjusted, or it's tuned such a way that the marginal distance between the distance between the closest point of respective classes is higher. So that this distance we are calling as a margin. Okay. And this line, this dotted line, it calls as an marginal line. Let me. Okay. So this line is an marginal plane. This is an margin, means distance. So this is also same, right? This is also same. The margin distance. This is also marginal plane, like this line. Okay. So this is the actual concept we have seen in this week lectures, right? So yeah, so the whatever process we have seen here, that is an hard margin plane. So this is an hard margin. So there is a no instances or points we have allowed in between the hyperplane and this marginal plane. So we have not allowed any points in between this uh, hyperplane and one second. Hello, I'm audible. Anyone please reply here. I'm audible. I hope I'm audible. Okay. So yeah, so that is the, so this is the point, and we are calculating the distance between this hyperplane. So that is an perpendicular distance between uh, this new the closest point and the separable boundary actually. So yeah, as we have seen that in this explanation, we got as an answer directly, which is an, you can see the C option. It states that clearly the perpendicular distance from the closest point. It defines that that is in a margin of a hyperplane. Okay, so this is the perpendicular distance we are calculating from this closest point. Okay, so this is from the perpendicular distance from the. Okay. So the how the distance we are getting, that is, and we have seen that is 1 divided by 2 and magnitude of w. We have seen this uh, in our lecture, right? So that is, we have taken the difference between the this point and this point, and then we are getting as in uh, this magnitude. Okay, so option C is correct here. Okay, let's move to the another question. Is there any doubt in this question? Yeah, maybe let's move to the another question. Yeah, so here the hard margin terminology comes into the picture. Second, here you can see the hard margin comes into the picture here. Right. One second. So
Excuse me, sir, you're not audible.
sorry, yeah, thanks for the coming. Yeah, thanks. Yeah. So okay, I will repeat the things whatever I have said. So we have whatever the explanation we have seen in this week, that is for the binary classification, and the SOM actually works for the both of the class task, such as the regression task and the classification task. In the regression task, we primarily predicting or detecting actual value of the instance or record, and the classification task, we are classifying instance or record in a classes, which could be a binary class or it may be a multi-class classification problem, right? It works for both of the class, but we have seen only for the classification. In specific, that we have seen for the binary classification, for sake of simply for sake of understanding, simply understanding. So yeah, so whatever the process we have seen for the SVM, the support vector machine, which we have discussed about the hard margin. Okay, so whatever it is, uh, drawing a hyperplane, and beside of that hyperplane it is drawing a marginal plane, and that marginal plane defines that the distance between the hyperplane and the closest point of a respective class, right? It should be maximized, right? And that hyperplane, so these terminologies are there. Here we are clearly dividing, or clearly drawing a separable decision boundary, and that decision boundary we are calling as an hyperplane. Okay, and we are not allowing uh, any instance, any training point uh, in between the hyperplane and the marginal plane. Okay, let's see here what we have seen right now. So this is an, let's take as an x2 feature, and this is an our x1 feature. So for records, and we have a lot of training records are there, or objects are there, we can see that. And based on this object, those records has an two attributes, or two attributes or features, x1 features and x2 feature. So we map these attributes in a 2D plot, because it has an two-dimensional features. So this is my classes. This, the two classes are there, and this primary class I have mapped here based on the x2 and x1 feature. And this is the second class, which we can also see that this is an uh, negative line, negative class, or this is an positive class likewise. So we in the support vector, we are primarily drawing a separable boundary line. And how we are drawing this from boundary line? Based on the marginal plane. So this is an support vectors, which are the closest point from this marginal, from this hyperplane. And this is our marginal marginal plane, which is passing from this support vectors, right? So these are the marginal plane, which is passing from our support. So this is an hyperplane, this is our marginal plane, this is margin, this is the margin, means it is a distance between the hyperplane and to the closest point of any class. Okay, margin. Okay. So it that the our objective is that to maximize the distance between, maximize the margin actually. Margin means that the distance between the hyperplane and the closest point. So it, why we require to maximize the margin actually, right? Because we require a generalized decision boundary. Okay, suppose I draw a decision boundary here, like this way, which has a marginal distance is very less. Okay, we randomly draw here. You can see marginal distance is very low as compared to this line. But in future, in our prediction task, okay, in a new instance comes into the picture, which is fall here. Okay, so according to this blue line, blue decision boundary, it classes to the negative class, that is an circular class, but it is actually from positive class, right? So this is not this is an strictly following this line actually, that is an, it does an, it can make a misclassification in the future. It's not sure than generalizability actually. So that to maintain the generalizability of the model, we have to draw a line such that the distance between the support vectors. So what are the support vectors are here? So this is an support vector here, this is an support vector are means these are the closest points from the hyperplane. vectors. Okay. So the distance between that hyperplane with the support vector, it should be maximized. That is, and margin should be the maximized. So here you can observe that there is a no uh, any point falls into this in between the margin and the hyperplane. We are not allowed here, right? We have to maximize. If the point is here, then we are considering this is as a support vector, and we are drawing a hyperplane such a way that the distance from this point to the hyperplane should be maximized, right? So here we are not allowing any points in between the margin and the hyperplane. That is called, it is, we are doing a strictly classifying, or strictly separating two classes, right? So this is the called as this we are calling as an hard margin support vector. So we are not allowing any instances or any training point in between the marginal plane and the hyperplane. So in the real world, actually, so you might be think that in the real world problems there is not uh, problems or situations are there that they are not clearly separable. Here we have explained, or we have seen the example that is an clearly separable example, right? But in a real world problem, there is most of the time it's not a uh, what we can see, it is not a clearly separable actually. So there is a some uh, or clearly separable, or there is a some in the future might be we are getting errors actually. Let's take one example, that is an, so this and 0 and this is an x. You can see these are very close enough, and some points are here, here is also, and here is also, it is like this way. Maybe we can call this problem as an overlapping problem. Means two classes are overlapping each other, some points only, not as an many points. That is, an, these points are here, this class, that is circular class, and this class is here, right? You can see there is no a separable space we are getting here, right? So in this case, we are drawing a hyperplane such a way that we are allowing some points in between the hyperplane and the marginal plane. So you can see, suppose I am allowing, that is an hyperparameter, that is an user defined value actually. How many points you have to allowed, or needs to be okay. That is an, if these points are in classified or misclassified, that is fine for me. Okay, because you are visualizing or aiming for a generalizability, right? That's why, suppose my c value, so this is and my how many points I can allow or misclassified while training the things, or all this misclassified, it falls in the marginal plane and the hyperplane. So if I given is a 3, so these points are act as a, they are misclassified, or so these points, so ignoring these 3 points, it is searching for another points which are act as a support vector, so in this case these are the support vectors we can call. In this case we can call the support vector this one and this one, because 3 points are like this. So support vector, so we are if we are if we are allowing these are the support vectors, then we need to draw a hyperplane, marginal plane from this point which is passing from this, and we need to maximize this distance, this margin, right? In this case, so this case is called as an soft margin, which is not strictly we are dividing the things. Okay, yeah. So considering whatever explanation we have seen right now, considering that, what could be the answer of this question too? In the hard margin support vector machine, Which option is correct for this question? No training instances lie inside the margin. Okay, that we have already uh, discussed here. The B option states that all the training instances lie inside the margin. Margin means this space. Okay, so here already mentioned margin means. Okay, and only few training instances lie inside the margin. None of the above. So, what do you think? Which option is correct for this question? Yes. Anyone? Anyone has got the answer? What do you think? This is very trivial. Yeah. Yes. The Yeah, many students are stating that the A option is correct. Yeah, so the A option states that no training instances lie inside the margin. Yeah, that is this is the situation we have seen here, right? So this is an hard margin, right? Hard margin, and this is a so these points are training instances. Whatever the points we have seen, the training instances points are there. Okay, okay. Let's move to the another question. I hope you guys understood. If you have any doubts, please let me know. Okay. Yeah, this is also straightforward, which has been in-depth calculation or intuition of this equation has been already taught in the lecture. So what could be the correct option for this question? So I repeat this question. The primal optimal optimization problem solved to obtain the hard margin optimal separating hyperplane is. So what is the our primal optimization problem? We need to minimize something. So what we need to minimize actually? Right. Also, our previous recent discussion, we have also seen what we have to. Uh, Actually, we have seen that what we have to maximize. But here, the equation has been written for the minimization. Right? But we have to maximize the distance between the hyperplane and the closest point, which is a margin. So here, it is written in the inverse form actually. So you can see which option could be the correct here. Yes, anyone? Okay. Maybe I will recall some things so that you will get some points to understand clearly. Yeah. May reduce the brightness. Yeah. So uh, we have points. Okay. So this is our hyperplane. This is our marginal plane. Support vector. So as we have seen that this equation, the equation of this line is n w transpose into x plus b is exactly equal to 0, right? Maybe you right now you recall that, right? So this is the line equation. And we have seen that above this line, the points above this line, which gets the value from this equation, is an positive, like positive plus 1, we can say that. That means, and the points on this line, that is appearing on this line, which, so appearing on this line, which is the value we are getting from this equation, which is an 0, right, that we have saw in the lectures. So as these points b is we are getting, which is an equal to plus 1. Okay, the sign we have seen mostly. And the equation for this line, for this margin that is below of the line, we are getting as an minus 1, right, that we have seen, transpose into x plus b, right. So these three equation we have write such a way that that is an x of I, that is an I. These are the number of training points are there, 1 to n, right? So we have considered a single point, that is a multiplication between these uh, yi, that is an actual label of that particular x instance, and wt into xi plus b is greater than equal to 1. So this equation satisfies this all the things. If the yi is minus 1 and our equation getting is minus 1, then it is an plus 1 we are getting, right? So if it is y is a plus 1, that is we are discussing for the binary classification, right? Y is an plus 1 and wt, this equation is it is giving as an plus 1, that is a that means we are getting as an plus 1, right? So this satisfies the both the condition. It ensures that we have an correct classification. So we have to draw a hyperplane such a way that all the training points get as an correct classification. Correct classifier means separable. If we got as a misclassification, misclassified by this hyperplane, that means our actual is an minus 1 and we are getting an plus 1, then this condition it falls, right? So that, so that we have to, this is our constraint actually, we have to allow this constraint such a way that we will get a correct classification or clear separable hyperplane. Okay, if it is not clearly separable, then we are getting the misclassification errors here itself. And the distance between uh, this two hyperplane and the margin, which is we have saw, that is an magnitude of w, right? 1 divided by magnitude of the w we have seen. So both of the so this one is 1 divided by magnitude of w, and this one is also 1 divided by magnitude of w, right? So we are getting as an magnitude w, right? So but we have multiplied with the actually this is an w only, and we require that this, the vector, this w magnitude, it includes magnitude as well as the vector, right? This the w2 two components are included, that is an magnitude, that is, let's write here two components, which is an magnitude, which is an ww, and that is a vector, that, right? So if you require, that is our equation is let's take as an w2, whatever ins we have, we got equal to, suppose is an 2 divided by is 2 difference, because this is a difference we are assuming that, and let's take as an here w, and we are dividing by the magnitudes, we are getting as an vector, because we want a vector actually. So this w we can write uh, in this way actually, because this is an w square, both of this including, right? W transpose into w, right? That means, so what this in detail of this equation we have seen step by step in the lectures as well. So observing this or recalling this explanation here, considering this, what do you think, which option is correct here? So whatever I have explained here, that is a clearly showing answer here, but I wanted to know from your side, what do you think, which one is correct option for this? That is our primal optimization problem for the hard margin optimal separating. What do you think? Which option is correct here? So I need to choose. Yes, anyone? Anyone has, or you have any guess? You may take a guess. Let's take a, because the answers are not coming. Maybe we'll try some guess. Or what do you think about this? Uh, our what is our goal actually? We need to. So here it is maximizing the vector. So our maximize. So maybe. So here the maximize margin distance we have seen that is in W, right? So this both of the this we can this maximize margin that we can write in a such a way that we need to minimize 1 divided by 2, because two distance from the positive class and what we can say the negative class, right? So we can write this W. The W means what? The W means here that is and the root of W1, because the distance we are calculating, that is a perpendicular distance from the closest point, the hyperplane, right? So that is W1 square and W2 square, right? So we are taking the square of this actually. So we can write a square, right? W1 into W2 and W1 into W2. So we can write also like this way, right? Minimum into W transpose into, sorry, W transpose into W, right? So now, yeah. So here that is a maximizing. Option B is an maximize, right? You can see the option here. It is not 1 divided by this term. If it is an 2 divided by this W transport W, then in that case maybe this is correct. But our task we have inversed it is and 1 divided by 2 into magnitude to square. So that is an magnitude square we have written, that is an W transpose. This is an W, okay, W transpose T, W transpose into W. So it is clearly mentioned that you can see the first option, it states that the minimize the this 1 divided by 2 W transpose into W such a way that we need to classify all the training points correctly. So this is for the hard margin. It is low margin, the soft margin, there is an C factor is introduced in the this term, which uh, ignores some instances. Other you can other value it is maximize, and other equation you can see it is a less than, that is it's wrong. It's also less than, because we have seen whatever the values we are getting as a less than equal to here, right? Okay, so yeah, maybe let's move to the another question. So this is an next step of that particular previous question. So previously that is two questions, two problems we have seen. That is in primal optimization and the dual optimization. Right? In the dual optimization, we have introduced a Lagrange's multiplier, right? That is an alpha value, right? And that alpha value, while introducing the alpha value, what we have done, our this yi into w transpose into xi plus b is greater than equal to 1, and in this case the yi w transpose into xi plus b, and then this one is we have shifted here and we have compared with the 0, right? And then we have introduced a Lagrange's multiplier, that is an alpha. Yes, have you recalled it? Considering that, what could be the correct option here in this case? So I have already given a half of the correct answer here, so that you may recall it, what we have seen in the lectures. Yes, anyone? Sorry. Yeah, it's correct. So yeah, some students has given the correct option, that is an option B. Here you can see that we are minimizing that previous equation, it is the same, but here we have introduced a Lagrange's uh, um, parameter to scale it out, and we can find by using this alpha w, we can find the b as well here. Okay, so maybe you can recall this question, this equation, if you wanted to deeply understand. So the last lecture you may watch again, maybe you will get as in that also, you will, if any doubts, so let me know in that case. Okay, okay, let's move to the another question, which is an question 5. uh, yeah, so the question states that Lagrange's multipliers correspond to the vectors have a value dot dot, means which value, right? So it is stating that this is our hyperplane, okay, or it is an, let's take support vectors. This is our support vectors, okay. This is our support vector, and there are some many points which are not support vectors. So they are stating that what is the Lagrangians, which means what is the alpha value for for this set of the points which are not support vectors. Sorry, which are not support vector. What are the alpha values? That is an Lagrange's multiplier for this uh, for these points. Yes, anyone? So the Lagrange's multiplier, which actually determines which points influence the decision boundary. Okay, that's why we have introduced the Lagrange's multiplier. Okay, so because in the KNN we have stored all of the points, right? Because all of the points we require, any new instances comes into the picture, so we are finding the distance between the all k points, k nearest points, and then we are finding which one is then higher votes, then we are classifying that is an this point is from that particular class. But in support vector we don't require the all other the training points. These points are we don't require, only the support vectors we require. That is very important, that we can store. And based on this support vector, we can predict any new future point, because this section is important. Based on these three lines, right, based on this marginal hyperplane and plane and hyperplane and the support vectors, based on this we are classifying this particular uh, any new point comes into any point that we can classify based on these concepts. That's why we require only the support vectors in the. So there is a no, the advantage of the support vector is and only requires the not requires many space to store that all the training points. Okay, so only the support vectors can we can store, and based on this support vector we can easily uh, uh, find or predict new points. Okay. So for the non-support vectors, which are the outside of the margin, means outside of this marginal plane, their Lagrange's multipliers are zero. Okay, means zero means right, yeah, the outside of this plane. And for support vectors which are aligning or which are incident on the margin, these are the margin, their support vectors are strictly greater than zero. Okay, strictly greater than there. So there is another different condition, that is and for the soft margin that we have not seen. Maybe in the next week we can detailed in the kernel mechanism, kernel intuition, that maybe we can see in the lectures uh, for the soft margin what could be the alpha value is changing. Okay, I hope you guys understand that the simple intuition is that the whatever the Lagrange's multiplier we are getting for the outside of the marginal plane, means for this value, those are the non-influential points for the decision boundary, right? So that's why their influence score to the decision boundary is a zero. The Lagrange's multiplier, you can directly or simply understand that the Lagrange's multiplier is nothing but the uh, influence, how much influence of that points on the decision boundary. Likewise, okay. So these support vectors, which has Lagrange's values, which should not be uh, less than zero or zero. It is always greater than the zero. Okay. So that here the option C is correct, greater than zero, because it is asked about the corresponding multiple Lagrange's multiple multipliers corresponding to the support vectors. Support about the support vector, it is asking the Lagrange's multiplier. Right. Yeah. I hope you guys understood, right? Yeah, see many students has stated Meenakshi. Yeah. Thanks. Okay, so our next question is the SVM are less effective when. So this is very trivial question maybe. So you may uh, answer which one is an correct option for this question 6. So I will read the question again. The SVMs are less effective when the data is linearly separable. Is it? Or the B option states that the data is clean and ready to use. Okay. Option C states that the data is noisy and contains overlapping points. None of the above. Let me explain detailed in these options. Maybe you will get a clear idea. Maybe some students got a correct option. They can answer in the chat box. Okay. Here, the first option states that the data is linearly separable, means there are two class considering there is, these are the linearly separable. There is a no, this class is incident in this class. Means this class is not incident in this class. Okay, or this class is not incident in this class. Right. So this is an A option. It is stating. B option is that data is clean. Means there is no noise in the data. You can directly visualize the data. There is no issue. Okay. There is a no any links or any uh, none values are there. The clean and very well suited data is there. Directly you can visual see. The option C states that the data has a noise. Sorry. Yeah. So here the option C states that the data has some noise and it contains overlapping points. That means let's take this one as a class one. This one is a one class. 1 second, some students are waiting. Okay. Yeah. So these are the points that we are already seen. These are the linearly separable. Overlapping points means these zero is a here and this like this way. The classes are merged. Subset of the classes are merged over here. That we can see like this way. And also some data has a noise. That means that data is some data is very apart from this distribution like this. Or option D is none of the above. None of the. So considering these three options, I have simplified the three of the option. What do you think which option is correct for this question? It's very trivial. It's straightforward question. Yeah. Any other response? Less effective. Yeah. So option C is correct, which is very trivial and straightforward. It is an overlapping. In this, the problem is that how we can draw a hyperplane. So hyperplane or the decision boundary we are drawing easily in between the separable distribution, linearly separable points. Okay. So here linearly separable. Sorry. So here it is difficult to draw a separable line actually. Yeah. Okay. I hope you guys understood, right? Okay. Let's move to the last question. So yeah, please read this question carefully and let me know which one is the correct option. If you saw the lecture videos, uh, so you will get easily what could be the which one is an correct option. Yeah, yeah. Some student has given the option. Maybe anyone has any other possibility of the answers, they can reply in the chat box. Yeah. So yeah, the Meenakshi has given the answer. That is in the dual optimization problem we are solving using the quadratic programming, which is straightforward. Yeah, maybe you have understood the support vector. The main intuition is that how we are classifying the points using the support vector, the process of support vector that you should know. I hope you guys know about the how the SVM works for the, at least the binary classification. And for the, so there is one, okay, I will recall some points. Maybe some students is not understood. Maybe only they can understand only these things, the basic things. We have a problem that we need to classify two classes. Problem is that binary classification. Binary classification means you have a two features, x1, x1, x2, and a class, correct class. Okay. So this is object 1, object 2, object 3. This is class 1, this object 2 class belongs to class 2, this is belongs to class 1, likewise. Only two options, two classes are there, class 1, class 2. For this problem, we are also stating that it is an binary classification. Okay, these are some values are there. So we need to train a machine learning model such a way that new object k comes, it is in training. So training maybe like this, I have mentioned, so this and symbols, but it's fine. Okay, so the new point comes, we need to classify it is either from c1 or c2. Okay, so we need to pass this object which has on x1 and x2 feature. Okay, we don't know exactly which class it belongs. We need to predict from our machine learning model. Our machine learning model, this is that is an we are also calling as a data mining technique or model. So using this previous data, this is our historical data, it will train, and based on this historical data, it will predict that this object k belongs to c2 class. I'm only for sake of a simple example, I have taken this c2 class, maybe it is from this c1 class. Okay. So such a way that, so this is the overall intuition. Okay. So we'll see the inside of this ML model. Okay, so here the inside it is that, so we have a two features, x2 and the x1 features. Firstly, we are mapping all of the features. This is an training data. From this training data, we are mapping this all the features here. We have a plus positive class, that is c1, maybe let's take as a positive, this one is negative. Positive class, and some is a negative class, another class. Okay. So this is a distribution we found, and we have plotted just on the 2D plot. Okay. So the what SVM does actually, it draw a hyperplane such a way that draw a hyperplane such a way that the distance between closest point from respective classes should be maximized. Should be, this is an closest point from this hyperplane, right? The distance between this margin, this closest point should be higher, right? Maximum. So we are drawing also a marginal plane as well here. So this, which is passing from this closest point here. Okay, this is a marginal plane. This closest point we are stating as an marginal or support vectors. Support vectors. That's why we are, because that's why we are calling this algorithm as a support vector machine. Okay. And this line is an marginal plane. marginal plane. So this one is an hyperplane. We are hyperplane, which is an separable decision boundary. Hyperplane. Okay. So yeah. So these are the terms, and so this process we are calling as an hard margin plane. Hard margin plane support vector machine. Okay. There is a soft margin plane also. So this is the two ways we can train our machine learning SVN support vector machine model. So the first is an hard margin and another is an soft margin. I hope you guys understood. Okay, so here suppose the new point comes. Suppose here, let's take as in here. This is our new point. So based on this support vector hyperplane, our support vector machine trained on our training data can easily classified it is belongs to a C2 class, because this minor denotes as a C2 class, right? Any points, if it is from here, it is directly from. It also make a misclassification as well. Means there isn't some uh, in our real world situation. There is some outliers are there. Outliers means this positive feature object maybe occurs at this point as well. Okay. Let's take as an that is an X-ray blockage classification, that particular X-ray has a blockage or not a blockage. Okay. So for a regular person, for regular patient, it finds we can find a different distribution. But a person who has a cancer, might be their X-ray is different, right? And it is from a positive class as well. So like this way, this like those persons are maybe falls into the um, what we can say outliers. Okay, so these are the outliers. Maybe in that case, this maybe uh, uh, do the misclassification problem. Okay, up to this, maybe you guys understood what exactly the simple intuition about the support vector machine, right? Yeah. Okay, maybe in next week, Dr. Pabitra may will explain about the situation where they are not linearly separable. Here, you have seen that these two classes are linearly separable. You can write a linear line and they are directly separable, right? But there is might be a one case such a way that you can see these are positive classes are here and the negative classes like this way. So here, how you can draw a separable line here. So as you can see, this situation, this example case we have seen, that is a not linearly separable points. But in the SVM classifier, it has some mechanism to classify these points in a better way. I will give a simple intuition so that you have some curiosity to watch next week videos. Okay. So in this case, what exactly support vector version acts like? Suppose it is there is a one kernel function. So right now it is an 2D dimensional. Okay, this is an x2 and x1. Some kernel function k function is there, and you are only passing this data from this kernel. It converts lower dimensional data to a higher dimensional data. Okay, so that you will get a point such a way that, so here the minus points are getting and the plus points are here, right? So it is in 2D, it is in 3D. We are increased the 2D dimension to the 3D dimension using a kernel function. There is a big deal about the kernel function. Only you have to scale your values to a three-dimensional vectors. Only you are multiplying some values with the already existing training points, so that we will get a higher dimensional data, and in that we will get a separable, linearly separable point. So here you can see, you can see this distribution are simply shows as an linearly separable distribution likewise. So in this case you can draw a hyperplane such a way as this, like, and these points may be support vectors here. Understood. So yeah, these are the some basic intuition about the non-linearly separable points. Yeah, in detail, you can in the next week, Dr. Pabitra will explain in detail very well. Okay, if you have any doubts in that, let's meet in next week. Okay, so yeah, that's it for this week. Right now, we have discussed.